have our picture of three charges. Two of them are labeled, 15 nanocoulombs and negative 5 nanocoulombs. The bottom right charge Q is negative 10 nanocoulombs. We want to know what the magnitude and direction of the force on Q is. So the force on this one. Now, certainly all three charges will be filling forces. Okay? This one will be filling force, this one will be filling force. But all we care about is the force on this one. So you don't have to worry about what those guys up there are filling, only what this one is. So our equation we have for the force on a charge, a point charge due to any other charge, depends upon the magnitude of the two charges involved, depends upon how far away they are. And then remember, force is a vector, so we'll need to write it in terms of its x and y components. So this portion gives us the magnitude of our force. So let's do the force on Q due to the negative 5 first, because that one's going to be easiest. Since they're both negative, what direction is the force on Q going to be in? Straight down. I'll call it F1. Now, yes, the negative 5 will be filling a force as well, but that's not pertinent to the question. We just want to know what the net force on Q is. So F1. We know K is 9 times 10 to the 9th, or 8.99 times 10 to the 9th. The two charges, Q1 and Q2, are the charges here. So Q1 is 5 nanocoulombs. Q2 is our 10 nanocoulombs. I'm just putting in the magnitude of these values because I'm going to put the direction on separately. R, the distance between them, 1 centimeter, so 0.01 meters, and that needs to be squared. That point out something. So plugging that all in, we get for this one 0.0045 newtons. That's just the magnitude though. In order to find the net force on Q, we're going to need to add the forces together, and since they're vectors, we have to have them written in vector notation. In terms of IJK, since it's straight down, that's the negative J hat direction. So you do have to get the direction on there with it. So magnitude is easy enough to get. The force on Q due to the 15 nanocoulomb charge, number one, we're going to need to know this distance. So that's what R is in the equation. R is the distance between the two charges. We know this side is 3 centimeters and this side is 1 centimeter. So using the Pythagorean theorem, 3 squared plus 1 squared square rooted. So we get 3.16 centimeters. I'm just going to keep a couple decimal places as we go along. So F2, what direction is the force on Q due to this guy? It's either towards it or away from it. Towards. So F2 lies along that hypotenuse line. Magnitude's easy to figure out. 9 times 10 to the 9th, Newton meter squared over Coulomb squared. The two charges involved are the 15 and the 10, so 15 nanocoulombs, 10 nanocoulombs over distance squared, so 0.0316 meters, quantity squared. So the magnitude of this force is 0.00135 newtons. But before we can add our forces together, we need to write this one as a vector as well. It has to be in terms of its x and y components. The 0.00135 is the hypotenuse here, 0.00135. But this force has an x component, and it has a y component. If we have the hypotenuse, we can easily figure out what that angle is. To get the x component, we need to take the hypotenuse times the cosine, because it's adjacent to our angle. So our x component will be cosine of theta. Since it's pointing to the left, it's negative I hat. Our y component is opposite our angle, so opposite is sine theta. So we're going to take our magnitude times the cosine to get the x component, our magnitude times the sine to get the y component. So we need the angle, or we need to know what the cosine of theta is. If we look at this big triangle here, if we look at that big triangle, what is the cosine in terms of the dimensions of that triangle?
949. 3 over 3.16.
Right. So 3, the adjacent side over the hypotenuse side. So this is 3 over 3.16 would be what the cosine is, which may very well be 0.9, whatever. So sine would be the 1 over the 3.16. So our cosine, negative 3 over 3.16, I hat, sine 1 over 3.16. That's our j hat component. Now there's nothing wrong with figuring out what the angle is and just taking the cosine of it and the sine of it. That's fine too. Are you okay with this? Okay. So what that does, if we multiply these out, F2 has components of negative 0.00128 newtons I hat, and then the y component is 0.000426 newtons j hat. We have to have our forces in vector notation in order to add them. The net force is simply the sum of these two. This one doesn't have an x component, so the x component is still going to be negative 0.00128. We have this y component and this y component. When we add those together, we're going to get negative 0.00407. So those are the components of our force vector, our resultant force vector. It's to the left by 0.00128 newtons. It's down by 0.00407 newtons. So our force vector looks like that. Now this is vector notation, so we're not done. This is not magnitude and direction. This is vector notation, this is component form. Magnitude means we want to know what the hypotenuse of this is, and direction means we want to know an angle. So hypotenuse, we know the x and y components meet at right angles. Using the Pythagorean theorem, x side squared plus y side squared square rooted, our magnitude ends up being 0.00427 newtons, or 4.3 millinewtons. Our angle, if we know the tangent of our angle is 0.00407 over the adjacent side, 0.00128. So theta, we get 73 degrees. But we need to specify. If we were to say our answer is 0.0043 newtons at 73 degrees, that would imply that it's up in the first quadrant. Because remember, in terms of polar coordinate systems, the angle is always measured from the x-axis. So we need to specify. Either we can say 73 degrees below the negative x-axis. That's what it is, negative x-axis at 73 degrees below there. Or we can add 73 to 180 and just say 253 degrees. That's fine as well, either way. But something somehow represent that it's in the third quadrant.